people engage, it enriches people, and it's very simple, just a way to disperse information to everyone. So I'm going to be presenting on the history of computing. We're having a few stream issues. We stream everything on Twitch, so if you want to follow us there, I'll link the appropriate social media later. So before we begin, why don't I ask everyone, what do you think a computer is, right? You know, you have any ideas? What does a computer mean to you guys, right? Is it something that you use every day? Do you have one in your pocket right now?
I think it's something that is created to make the thing that you want to do easier.
Perfect. It's a good example. A computer is a tool that lets us do things computationally, right? Whereas a hammer would let us physically knock in a nail. A computer can let us run a program, run an algorithm, let it compute information in a way much faster than us people. Fernando, are you ready to go? Okay. So that's what I'm about, the history of computing. So as I said before, these computers are tools, right? And these tools are a summation of multiple different parts. In this picture, we have a hard drive, we have a CPU, we have a motherboard, memory, all these different components. Did I do that? Whatever. But where did all these components come from, right? They didn't just appear out of nowhere. They had to have had a history, and there's a long and complex history that humans have had since the beginning of time to better organize and quantify the world around us. So that's where we're going to begin. This on? Oh no. Unscuff, please. Basic definition of a computer, right? This is a very robotic definition of a computer. It kind of matches the computer, the essence of what it does, but I don't think it captures the spirit or what it symbolizes, right? A computer is an electronic device that can be programmed to carry out a sequence of arithmetic and logical operations. Pretty simple, right? Every program is just a combination of ones and zeros at a very low level that have some sort of logic built into it so that you can create something. A lot of computers today, sorry about that, have a lot more abstraction from the hardware. Everything is kind of cloud-based now. Everything is based on a user interface so that everyone can use it really easily. That's why, even if you don't know anything about computers, you can easily pick up a smartphone, load up an app, watch some YouTube, do whatever you want to do, right? I found this quote by Isaac Asimov. He is a science fiction writer, and he says that he doesn't fear computers, but he fears the lack of them. And this is because computers have become so important into the 21st century mindset and reality. Everything happens on computers, simply just the phone, right? Everything is centered around this one idea of a computer. But where did it all begin? All the way back in 2500 BC, that is around 5,000-ish years from today. In China and Mesopotamia, we came up with the first counting tool, which is the abacus. Or this is like the first documented tool. There was other things beforehand. And the abacus is a very simple tool. We give it to kids, and it allows us to measure information in higher levels of complexity, right? So with the abacus, we have these different rows, and you can count 1 to 10, and then what you can do is that you can shift up one row to symbolize that this is now in the tens place, this is the ones, this is the hundreds. So before, we counted on our fingers, we don't have a million fingers, but because of these organizations of information in space, we can start counting up tens, hundreds, thousands, 100,000s upwards, right? Because of these organizational tools. This uses a base 10 counting system. That means that we count 1 through 10, and it lets us represent large numbers. It was helpful for people paying their taxes, paying their debts in ancient civilization. Exactly. What was the next abstraction from that, right? In India, in 200 BC, the mathematician Pingala, he came up with this idea of a binary system. And binary system uses base 2, which is very important for computers because it's really easy to measure things as on or off, high or low, true or false. This is the logic that would later become Boolean logic, which you might have heard of. And the idea is that we can represent two numbers. So I have a little thought experiment for you guys, right? Take out your hands and just think about how many numbers you can count up to, right? 10? Right. Now, with the binary system, right, we have our 10 fingers, but if we represent one finger as a true or a false, we can get 2 to the power of 5 on one hand, which is 32 minus 1. We can count up to 32 with one hand, right? So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, yeah, 19, 20, 21, and so on, right? And if you have the other hands, you can count up to 2 to the power of 10, which is 1,024 minus 1, 1,023. The idea here being that if you have these different bits of information, you can count much higher levels of complexity with very simple information. So usually when we think about a computer, information is split into an 8-bit byte, and that is the most basic building block of every computer today. So this came up in 2000 BC, 2,200 years ago, and it's still relevant today. But in terms of actual counting and computation, the first manual computer was created by Blaise Pascal. He was a mathematician. You might have heard from him in your geometry classes. And he came up with the Pascaline. This is a very basic calculator which used a bunch of compound gears in order to add and subtract numbers. In the same way that the abacus, you could represent a second row, like the tens place with the second row. You can represent the seconds place with a higher gear or a lower gear of a 1/10 the ratio. And by doing this, you could additively subtract and add, which means that you can multiply and divide with some level of complexity, right? But this wasn't good enough. So we have Gottfried Leibniz. You might have also heard him if you took in a calculus class. He came up with that one interpretation of the chain rule. And he came up with this big old calculator called the Stepper-Reckoner. I think in German it's the Staffelwast as its name. I probably butchered the pronunciation. And this thing could perform 8 and 16-digit number calculations, multiplication, addition, subtraction, and division. And this came up with the first idea of the algebra of concepts, which would later evolve into our Boolean arithmetic, which we'll discuss later. Now we're going into, so this is 1672, right? We're going into about 100 years later, and we came up with this one idea of the difference engine and the analytical machine. This computer right here is the basis for the next 100 years of computation. And it was never created because people, they didn't want to put money into it. But if they built this, I'm telling you right now, up until like 1935 or 1950, right? Every computer followed this basic idea, just with much smaller parts of different complexity when the technology evolved, right? And this thing was using steam power and little punch cards as a way to give a very basic program that you could use as a sort of computer memory. And this would allow you to do different addition, multiplication, logarithms. It would crunch them out really in about like a minute or two. It was pretty long, but it was pretty good. On this same time, we have the first computer scientist in Italy. Ada Lovelace came up with this algorithm for that previous machine, the differential engine, right? And the analytical engine, sorry, because this is the second one. And this algorithm became the first idea of someone using data analysis or somebody using any sort of algorithm on a computer, which is pretty cool. This is the birth of computer science by a woman. You got a question?
The computer that you seen in the first slide, was that ever actually made, or was it just not mass produced?
This was a replication. The first differential and analytical engines were never produced. They were all theoretical. But this would be the first theoretical algorithm for it. I think in the next coming years, we actually see the applications of the knowledge given from the differential engine into something actually created. So this is our good friend George Boole from the United Kingdom. And in 1847, he came up with the idea of Boolean algebra. This is that same logic that we were using a long time ago, but it's more streamlined now. So now we have logic. And this logic was the 3 gates and, nor, and not, right? And these can compare states of ones and zeros in order to make a big table. If you've ever taken a computer science class, you might have seen these. They're not really something that's fun to go into right now, but they are very effective in creating computers. Almost all computers today are created off of these three gates and a few others that were invented later on. But you could represent any system of equations, any sort of information with these 3 gates. Now we have the census tabulator. So the 1880 census took 7 years to calculate. And if you know anything about American history, it takes 10 years. You do the census every 10 years, right? So by the time the census was 3 years around, they finally figured out how many people are living in places. This is awful. So Herman Hollerith, he came up with this electromechanical computer. This would be the first electromechanical computer, and it used punch cards as a way of determining how many people were there. So what would happen is that these little pins, they're kind of hard to see, would be pushed down on a piece of paper, and like a little spring would be on top of it. If electrical connection was made, then it would count the person, and if not, then we know that there's no one there because the little cards aren't there. This helped out in speeding up the creation of the census data incredibly, and this guy would eventually create the company we know as IBM, which is a massive computer manufacturer. In 1918, we have the flip-flop. The flip-flop has a kind of funny name, and what it is, it's a 2 connected NOR gates. And while I don't want to explain exactly how this works, the idea here is that you can set and reset a value of 0 or 1. And this is very important because every modern computer from now on uses a system of the flip-flop because that's what we need to set our data, right? If we want to write a code, we save that information, it sets a bunch of 1s and 0s to whatever value it needs to be, and that's how we get our programs that we want today. This is the Turing machine, which is the first application of the SR latch, the flip-flop. And what it does is that it is a machine that can read, write, and move back and forward in order to set data. And every computer from now on, or not in this presentation, but every modern computer kind of passes the Turing test. It can edit values 1s and 0s as a way to write states and then program logic onto it. Yes?
I call the Turing test also the one, the AI one?
Yes, that's also the one where these machines are considered Turing positive. The Turing test is also the CAPTCHA, the automated Turing test to tell humans and computers apart. That is a application in the 1950s that Turing also says. It's a further explanation, and that is all about how much human-like behavior you can get out of a robot. But they weren't thinking of AI to that point. They were just thinking about how...
You seen the test of the first... they did it in physics, but it was basically back in 1930s, before the 40s, there was pre-programmed responses that a machine would do. Like someone would say something, and then you see this?
No, I've not seen that, but...
There was pre-programmed responses. Someone would say something, the machine would detect whatever this person said, and it would respond something back based on like basic conversation, and they would say a person, go talk to this thing, and they're gonna talk to you back, and basically it would just run through like a dialogue tree.
Yeah, so it's like a little dialogue box. I would assume that would come in the 1950s because right now these computers, but maybe.
But the thing is that I think it was like 80% of people could not tell if it was a robot. Like even back then, they couldn't even tell like they already had mapped out like what a dialogue tree was back then. Like people couldn't even tell that like they were talking about a super.
In 58, Turing came up with the idea of the Turing test, which was probably based off of that idea. But this is like the Turing machine, which is a theoretical device, which is the application of the flip-flop, which is all of our computers today. In 1938, we have the German Z1, Konrad Zuse. This is the first programmable computer, which uses the logic gates in order to do things, right? And the memory was stored in punch cards. You put them in, similar to the census tabulator, but this one you can actually program it to do multiple different functions. The census tabulator was only designed to index numbers for populations, right? We have the Harvard Mark I in 1980, and this is the second program-controlled machine. And what I want to make note of here is that this thing was a monster. 75 feet long, 5 tons, 750,000 parts. This thing, these are only like snippets of the entire room that this thing would take up. And the reason why it was so massive is because of these large vacuum tubes, which are used as the sort of logic gates for now. They're these vacuum-sealed glass bulbs. And because of like how a light bulb works, an old incandescent bulb, similar logic was used, and then you could put a voltage through it, and then if it was good enough, it would pass, and then it would create like a signal. These are the vacuum tube computers. We have the ABC, the UK Mark I, the ENIAC, and the EDVAC. I didn't want to go through these in too much detail, but this was the first computer to only use digital parts. This was the first computer. This one solved the cipher for in World War II. This isn't the Enigma solver, but if you know what that is, this was the first fully programmable computer where you can write whatever you wanted to into it, and it would program itself. This was just a larger version of the ABC, and then the EDVAC was the first computer to have actual stored memory inside of it, which I think is pretty cool. So at this point, computers are massive. What makes them smaller? The transistor. The transistor are these little components. You might have seen them around if you've worked with little circuits. Essentially, you can apply electricity to two sides, and it can select a state to this middle shaft. And this decreased the cost and size of computers because you could remove entire vacuum tubes, which are like these big light bulb shaped objects, probably like the size of a water bottle, into one of these little circuits, right? And this was invented in 1947, and this became the standard for technology up until I think around the 60s. I mean, yes, question?
Yeah, I don't know if you mentioned it, like in the late, but I know where the computers are a lot larger. I just want to say that. The reason they're called bugs today is because back then they physically got bugs inside.
Yes.
Off of the computer.
It was actually, unfortunately, my mouse control's been yoinked, but I can show you the exact machine where. Let's see. Go back a few pages. It was the. No, it was the Z1 that had the first memory bug, I think. And from there, you could create. That was where the term debugging came from, and that's where all of this cool stuff came from. Yeah, there was a literal fly inside of a board that covered a connector, and that was what created computer bug. The computer just didn't work. So there's a bug in it. And now we have new hardware and tools, right? So the modern technology, before memory was on punch cards, storage was on was also on the punch cards, it's all stored together. And what we ended up doing was that we created RAM, which is like the temporary memory that was used in computers today. You get a stick of RAM. Of course, this was using a magnetic core. Now we use solid-state RAM. IBM produced the first floppy disk. These are like these really old standards for storing memory. We ended up moving to hard drives, and now we're using solid-state memory there as well. And we created the assembly program language, and later on Fortran, which is the first programming language that you could like actually type in words, and you would be able to control a program with words. Assembly was using machine code, so you'd use different addresses. It's not that much fun, but it was what we had to do before then, right? Then came the generation of the integrated circuit. Beforehand, with transistors, you had to solder them all together. It was better than a vacuum tube, but if you ever like accidentally crossed a connection, the computer wouldn't work, right? Some bit wouldn't be able to do anything. So that's when we came up with the integrated circuit. These are these small little boards. If you've ever seen an Arduino, there's one little integrated circuit on it that looks like this, a little centipede-looking thingy. And these are the current like standard for our robotics and computers today. What ended up happening was that because transistors could get so small, this guy named Moore, he came up with this idea that processing the density of a transistor would double every 2 years. And this has been proven true since the 1970s all the way to 2020. These chips get so small that the charges that go between the little lines, the little circuits, wire, they will actually affect each other, these two charges, and they will cause information to be destroyed. That's called quantum tunneling, which just shows that we are almost near the capacity of transistors, right? But we probably have like another 10 years before that happens, right? But these computers still very centered around people that have degrees, people that study this for their lives. In 1974, we had the first personal computer, which used this one microprocessor. Not that important. People don't really think about it too much, but I want to mention it. 1984, we have the Macintosh, which is created by our Lord and Savior Apple. And this was the first consumer computer where you'd have programs loaded onto it. You could do things like browse the web. You didn't have to know what a computer was in order to use it properly, right? And this is the beginning of computers as a consumer product, as a thing that we have on us at all points, which is very important because where would our current civilization be without it? What's up?
Wait.
Hmm?
You have a camera for the audience now.
Huh? There's a microphone there.
The audience
For you.
Oh, okay. I'm doing a presentation on Apple next week, and I am talking about the Macintosh too. I know you're not talking about software, but you have to mention how the software in the Macintosh was the most user accessible, which was what really made that that personal computer. Oh, he has it there, made it more mainstream.
Exactly.
Because computers were like present, but it was really the operating system that really got people to like learn it because it was so simple. At least the Apple one was, compared to the other computers at that time.
Yes, and this model of simple design, very easy to use apps is kind of what drives a lot of technology today, right? Everything is so abstract, from writing zeros and ones and solving little punch cards with all these little bits of information. This is the personal computer. This is consumer electronics, right? So I'm going to wrap up this presentation a bit. We're talking about computers today. Because of Moore's laws, our computers are really small, size of our pocket. If you took a phone from today and you took it to like the time of the moon landing, you would have 1,000 times the processing power. Everyone would think like you're a wizard or something. It would be crazy, right? Yeah, lightning bolts shoot from your fingers. Like, it would be that crazy. The cell phone, currently, I keep mentioning it over and over again because I can't emphasize how incredible it is that you can have a computer this small located within your pocket, right? I think that's so neat. In conclusion, the computer is more than just a data processing tool. I think it's symbolic of humanity's long quest in order to better understand and quantify the world. We started all the way back in 2500 BC with people moving little beads on a wooden stand, and now we have the ability to go into space in order to simulate mind, in order to do all these things. Future technology might involve quantum computing, which is something I'm not going to discuss too much. In 2016, MIT, or I think it was MIT, one of these tech people, they came up with a 5-atom quantum computer, which is kind of cool. I don't know how to explain that to you, but that's essentially our outlook of technology. We're going to have Moore's law eventually reach its eventual limit sometime soon. Transistors are going to get really small. We're going to have really cool computers. Everyone's going to be happy, and that's it. Oh, we got a question? I'm not going to talk about architectures, but if you want to talk about that, sure.
No. I thought GC computers today, you're not gonna usually just talking about today.
No, because this is a computation. I mean, we could talk more and more about every computer that was released, but you have to be a little bit brief. I don't want to make this too long.
Right.
But if you want to talk more about it, sure. Okay, then. Well, that's it for me. Thank you all for listening. Any questions, anyone? No? Perfect.